Welcome to Unchatted Waters. In this episode, we explore how our ocean moves, from waves crashing on the seashore to the ocean conveyor belt moving across the globe. If you find yourself looking out at the sea and want to understand more of its secrets, join this episode and you may just uncover a treasure trove of information hidden in a message in a bottle. Welcome to Unchatted Waters, the podcast that talks to the people behind the science. I'm Kirsty, your host, and I'm excited to introduce my two guests for today's episode. Piyali Chowdhury is a senior coastal scientist studying the impacts of climate change using data-driven methods. She investigates risks and helps to improve warning systems around the coast. Stephen Dye is a principal marine climate scientist working to understand how the ocean fits into the climate system. His work explores the interactions between ocean and atmosphere so that we can predict how climate affects UK ecosystems. Welcome to the podcast.
Hello.
Hello. Great to have you here. So my first question is for you, Stephen. And what is physical oceanography?
Well, so at its very basis, I guess it's really how the sea moves, why its properties, so its temperature, its salinity, its density change, how it interacts at its boundaries. So that might be with the atmosphere above it, it might be the land at the edges, it might be the land underneath it, or it might be the ice at the edges or on top of it, and it might be the rivers that are flowing into it. But how's it interacting with those boundaries? And then what we really want to know is how the ocean contributes and responds to climate change, if we're thinking about the way the planet works. And then for physical oceanographers, if we can then get to the point where we can describe those mathematically and then potentially model them with computers, then that's the kind of encompassing most of what I think of as physical oceanography.
So, Piyali, how does the sea move in a way that we're familiar?
So when we go to the beach, we see the waves coming and crashing on our shoreline, but the waves that we see crashing are formed elsewhere. And before they come closer to the shore and break, they travel sometimes thousands of kilometers. And when they break, they release a lot of energy. And this is the energy that moves the sediments around. And that's how most of our coasts are shaped. Another aspect that moves the sea is the tides. So tides are the periodic rise and fall of the sea levels and are caused due to gravitational forces exerted between sun, moon, and the earth. For example, if you go to the Bristol Channel, the Severn estuary experiences the second highest tidal range in the world, which is about 12 meters.
So tides are in a short time frame, whereas your sea level rise is your average sea level across the globe.
So the sea level is measured based on a number of factors. Measuring sea level change is a combination of factors like how the land goes up and down, then what is the impact of tides, and also how the melting of glaciers are projected into the future. The sea level can rise or fall. It depends upon many aspects, but due to the ice melting and global warming of the ocean, sea level rise has been evident at many places, and it is also a reason how our coasts will be shaped in the future.
But it's worth exploring that how we experience sea level rise will be at our coasts. How we experience it depends on how the land that you're standing on is also moving. And over thousands of years, that's reacting to huge glacial masses of ice coming and going, mass on top of the land, like weighing it down. Oh, wow. And now the ice has gone, particularly say the north of the UK.
From the Ice Age.
So it's melted. And over the thousands of years since that's gone away, the land is gradually rising there. Whereas in the south of the UK, where there weren't glaciers, that land is sinking. And so there's a relative difference between the north and the south of the United Kingdom. And you have to consider that when you consider how the sea level that you experience at the coast is changing.
Wow.
So there's a difference between absolute sea level, the average change in the sea level in the ocean, versus relative sea level, which is relative to your location and the thing that you build your sea defences for and all of your infrastructure planning, which is how you experience it on the land.
That's so interesting that it's all those factors coming together. I would never have thought about the land's moved, because you're thinking about the sea level, but you've got to think about the land as well. That's really interesting. Okay, so we've got oceans, tides, sea level change. What about what you mentioned, Stephen, about the way that the sea interacts with the atmosphere? Can you go into some details on that, please?
Piyali has already mentioned it. So as the wind's blowing across the top of the sea, it's generating wave motions out to the ocean. Big swells then move towards the coasts, and we see them breaking. The wind is generating waves, but it's also generating large-scale circulation movement.
At the surface or at depth as well?
It starts at the surface because that's where they're rubbing up against each other, but then that extends down to a wind-driven layer. So there's a layer of the ocean that we expect to be driven by that wind in the ocean. So then it starts to interact with density changes, which is the other primary thing that generates movement in the ocean. Water in the south that's warmer, water in the north that's getting cooled. That sinks, that water needs to be replaced, and some of this water that's being blown by the wind is moving up and helping replace that sinking pathway. And so that adds to this big, large-scale circulation. That deep water then sinks, passes back into the rest of the ocean basins, and you get a vertical overturning circulation to go along with your mainly wind-driven horizontal circulation.
So would you say that at the surface it's like a conveyor belt moving things at the top, and then underneath it's like a vertical cog going round in circles? How can we better visualise it? Because you're doing great. He's talking with the hand gestures here. That's being really helpful for how we understand it, but how can we visualise it for our listeners?
So interestingly, the vertical circulation is the one that people tend to talk about as being the conveyor belt. So this warm water pathway north, sinking, and then filling the ocean basins, gradually rising to the surface as it warms through mixing, and then passing north again in very broad terms. So that tends to be thought of as a conveyor belt, this conveyor belt analogy. I haven't got a good one for the surface one, but it's kind of like a road, if you like, a pathway around.
It's being driven by.
I haven't got a good.
Yeah, it's hard. It's hard to visualize, isn't it? Because there's so many things happening in 3D.
Yeah.
So what does the ocean absorb from the atmosphere then? Because we've talked about wind.
Exchange of heat into or out of the ocean, directly coming from the sun or coming from interactions with the atmosphere above it. Changes in the freshwater content, the amount of salt in the sea. That's another primary way that the atmosphere influences the ocean, and that density circulation.
So is that from evaporation?
So that's you've got a balance between evaporation going out versus rivers that are bringing some fresh water back in, or melting ice at the edges, or rainfall. Carbon dioxide is being taken up by the ocean. Carbon dioxide drives climate change through the greenhouse effect, but there's a balance of the amount of CO2 in the atmosphere versus how much is absorbed into the ocean, and that can then join in and be locked up. If the ocean wasn't taking up carbon dioxide, then there would be more in the atmosphere, and there would be a greater greenhouse effect than we've already experienced.
So is it taken up by plankton, photosynthesis? Or
that's part of
why
it.
Does it take it away from us? It's very useful for us that it's taken it out of the atmosphere.
So it's a balance, something called partial pressure, but we're getting into chemistry then. A whole discipline of oceanography that's around the interchange of gases between the atmosphere and the ocean. And it's not just CO2, it's other gases as well, and other interactions as well. There's the physical pump, so there's physical chemistry, how much gas can be absorbed by a liquid.
Oh, okay.
That type of thing. But then there's also the biological pump,
right,
which is how phytoplankton, through photosynthesis, can take up carbon dioxide and bring it into the ocean. And then there's a whole set of biogeochemical cycles that then define whether you lock it up in the ocean. But
the ocean takes up carbon dioxide, and we'll put a full stop on the end of that.
Yeah, you need a whole different podcast, and maybe you can get to that when you talk about blue carbon.
Piyali, why do we need to know what the ocean is doing?
It is important to know what the ocean is doing, because just like Stephen said, we need to understand the processes that are happening in the ocean in order to also understand what is happening at our coast. So, for example, as we speak, there is a storm out there. So because we have started to understand the ocean well, there are methods and technologies by which we can predict such events and give warning, which is beneficial to the society. And also, understanding the ocean will help solve many interesting environmental issues, like how the global warming is going to happen in the future, how much of the ice will melt, what will happen to the sea level rise, and things like that. And understanding the ocean also helps us in predicting several natural disasters.
Yeah, because I think about how many weather warnings we've had in recent years. Is that because of climate change, or do you think it's because we're getting better at predicting this kind of adverse weather?
We have definitely come a long way, and now the prediction is accurate. But of course, the climate change has also a role to play. In the recent times, for example, the Arabian Sea, which is in the North Indian Ocean, did not receive many cyclones in the past. But due to the global warming, the Arabian Sea is warming up faster and is experiencing a lot of cyclones in that part of the world. So this is just an example to show you how climate change is also impacting these natural disasters. Of course, with the new methods and technologies, we have started to predict them as accurately as possible.
How do we take these measurements that Piyali was describing then in the ocean and then use that data to form these predictions?
So for temperature, the classical way would be to use a thermometer of some sort, putting down a rosette.
Jargon alarm. What's a rosette?
A circular frame, and around it you place 12 or 24 water bottles. On those water bottles, on some of the water bottles, you might place a thermometer.
We talked about ocean circulation and all the ways that the ocean moves and conveyor belts at the beginning of the episode. So how do we measure that?
It's always been historically very hard to measure, because imagine you're on a ship which is sat on top of a moving fluid, potentially trying to measure the circulation below it of the fluid that you're actually moving with.
Yeah.
And so it has actually always been a really hard thing to do, is to measure speed and direction beneath you if you're on a ship. So you've got two ways of measuring things. You can either sit in one place and watch the currents go past you, or you can follow the current. One way to measure it might be to leave something, to anchor it on the seabed, and then measure the current, speed and direction at one location at a particular depth. You would put something called a current meter in there and leave it there, put a float in the water, track that as it moves with the water itself. There are ones that can pop up back to the surface, send data back via satellite.
What was the kind of probably low-tech technology from history which really helped that happen?
People have tried to do that for a long time, so just throwing an apple into the water and watching where it goes would be one way of doing it.
As long as it's not a chip sandwich, then it won't get eaten by anything.
but so you can do that at the surface fairly easily, and people have done that for a while, but understanding how the interior part of the sea moves is really difficult. One of the really nice historical ways of doing it was a scientist back at the start of the 20th century. He came up with a way of weighting empty bottles just heavy enough that they wouldn't float at the surface and just light enough that they wouldn't land on the sea bottom. We wanted to know maybe where fish eggs might go after they've been spawned and where they might distribute to. So they used to put out these bottles, glass bottles, with a little bit of lead shot in and a postcard inside. When a fisherman picked those up, they were supposed to send back the postcard to the laboratory. This is where I found it. And then you'd have a trace of at least the start and the end of that journey. And one of my favourite jobs I've done was verifying the world record message in a bottle. It's no longer the record holder, but 10 years ago this was the world record, and somebody from Lowestoft had put a bottle off of one of our ships, and it had been found on a Danish beach. Guinness World Records wanted to verify the period of time that it had been in the water, so over a century in the water, and I was able to go and find the logbook of the ship, the exact position and the name of the person who'd actually put it in the water. Carried on doing those kinds of measurements through to the 60s, and we still get occasional returns back of those.
So Stephen's gone through a bit of the historical ways that we used to record some of these big aspects of the ocean. How do we do it now? Because surely technology is going to really have helped us in recent years.
Recently, we rely a lot on the buoys and sensors that we put into the ocean. And another way of measuring the ocean nowadays is the satellite images. So we do keep a track of daily images, and then we try to look at where the eddies are forming.
An eddy is like a piece of circular movement that kind of gets separated from the main circulation and then twirls off by itself in a little spin. Or a spinning top, that could be a good analogy. So like it's connected to the string, but then it gets flicked off and goes off by itself. Mm-hmm. And it's spinning.
If you think about weather, think of a hurricane or a big storm swirling around. It's a circular pattern. The same process happening in the ocean. It's just a denser fluid. In the ocean, those are eddies.
Which are a bit smaller.
Which are smaller than a storm because you're in the ocean.
And we won't get into the fact that they spin one way of the northern hemisphere and the other way, the bottom half. But that's just a fun fact. Yeah. We're too early for that. So before I interrupted you, Piyali, you were talking about technology.
The satellite images and spotting the upwelling locations. So that gives us an information of might be the hotspots for various biological activities. The other interesting way of measuring the depths of the ocean is unmanned vehicles that we put into the depths of the ocean. It measures the depth of the ocean, it measures temperature, comes back onto the surface, it sends data, and then we can analyze the data. Because a lot of data is being generated through the modern techniques, we have started relying on various artificial intelligent methods, get the crisp information out of huge amount of data that we are generating nowadays.
Okay, so at the surface, you have buoys that are floating around and providing their location to satellite?
Wave buoys are static in nature. So it collects the data and then it sends the data back to the satellite through these sensors.
Okay, so that's the same as what Stephen was describing with your current meter being in one place, just at the surface, and then it flowing past and just giving you the data back to satellite.
Yes.
And then your description of what's happening at the lower levels is with the unmanned vehicles, such as gliders, which are like little planes that go in between, and they go across like GPS track, I guess, that you've already organised, and it goes up and down, and it measures all the time, so you can get a real idea. Yes,
it measures the bathymetry of the ocean, it measures the depth of the ocean, it measures temperature at various levels. So these are some of the data that it can measure and then send it back onto the station.
And then does it tell you the currents as it's going past?
Gliders are primarily not that great at measuring currents because they're actively trying to move. They're gliding and steering themselves on a particular path.
And they're not passive.
They're not passive. So the other option are floats that can be set to change their density themselves, and so they can be dense enough to sink to a certain set level. Float around, follow the circulation pattern at say 2,000 metres, float up to the surface, send its data back, including its location, and then drop back down to the level it was, and you get to see its track.
Because I'm thinking of, as a fish biologist, I'm thinking about the sunfish with their fins in either direction kind of floating on the current, and if you could have a human-made version of that, that would be ideal, but it sounds like you've already got one. So I've always got to link it back to my fishy facts, and today we're going to have a fun fact or a nugget of information at the end of our episode to give our listeners something to take away, something interesting that people can tell their friends that you learnt on this podcast. So
if you ever look up on the internet for the world's largest waterfall, you'll occasionally find alongside Victoria Falls and terrestrial waterfalls, occasionally you'll also see pop up an underwater waterfall that happens between Greenland and Iceland in a place called the Denmark Strait, and it's where this dense water that's been cooled to depth flows over a restriction in the landmass between Greenland and Iceland, about 400 metres, and it's so dense that it's much denser than the water at the same level in the open Atlantic, and so it sinks rapidly down this pathway out of the Arctic into the North Atlantic. It's called the Denmark Strait Overflow, and we measured it for many, many years.
This is like an underwater waterfall.
Some people would consider it an underwater waterfall, and you'll find it on the internet called that. I wouldn't call it that,
okay.
But it has been
simplified
referred
it again.
to. It has been referred to like that, and this ties back to one of the things I was talking about earlier about how hard it is to measure these currents. Back in the 1950s, we were trying to find out ways to measure currents at depth because it was before we had electronically, and we needed a physical way to measure currents. And so people in Lowestoft came up with this idea where you would have another bottle, filled with two liquids with an interface between them. On deck of a ship, you would warm them up so that they were fully liquid. Once they were cold and in the interior of the ocean, they would cool down and solidify. And so those were attached to a line, dropped to the bottom of the sea. They would float up and be knocked down by the current that was going past them. When the interface between those two layers solidified, it would be at an angle. that angle would tell you how much the bottle was being knocked over and give you an estimate of the speed of the water going past it.
Okay.
But you also need to know the direction. So they put a magnetized disc of metal at the interface, and the direction that disc was facing when the liquid solidified gave you an estimate of the direction that the water was flowing as well. And so one of the first direct measurements of this Denmark Strait overflow was made in 1959, 1960, using this rather rudimentary method.
So you've dropped it down to the ocean, it's then been tipped over at a certain angle. How would you then record that if you're not down there? Would you then pick it up and it would stay at that angle?
Yeah, so you bring it back up, it's solidified now and it's stayed cool.
And you've brought it up too quickly for it to melt.
Yeah, it's not going to... So you warm it up, it needs to be warm before it stays at that angle, the disc in it, and then you can measure the angle. You've obviously calibrated that back at the laboratory, knowing what angle is what speed of water.
That's so cool.
That in the early 50s and 60s, before we had electronic measurements and ways of recording, that was a way of estimating speed of current at below the surface. Not perfect in any way, but I
love that they've found a way of measuring something quite complex back in time. It's like my favourite kind of retro. We've adapted technology so much now, but it's really nice to hear some of the examples back in history. It's like finding a typewriter in a charity shop. It's it's just so nice and tangible that they actually found a way to work this out. It's really interesting. But let's talk about technology. We're in a technological age. I think that's going to link to your fun fact.
So yes, I just spoke about collecting a lot of data and the use of artificial intelligence methods to assimilate these data in order to find information. So there is now a vision to create a digital twin of the ocean. It is based on the fact that we are collecting a lot of data, that is everything, everywhere, all at once, because we are collecting a lot of data from as many places as possible, and everything is being collected on the same time scale. So we have continuous time series of flowing data.
Wow.
So this then can be used to reconstruct the ocean digitally. And the benefit of doing that is we can monitor what is happening in the ocean on a digital platform, and then we can plug in some numerical models to see what might happen in various what-if scenarios, which gives us a very good indication of how the ocean will behave in the future under the various climate change scenarios.
Wow, so a digital twin is basically a digital model of the ocean. Are we close to that yet? Are we already doing that? Or is that kind of what we're hoping to achieve with all this data? Are we on our way? Because that sounds incredible.
Yes, so as you may think, a lot of scientific involvement is required. So people have started doing it on very small scales, but the vision of the whole ocean on the digital platform, which has all the data plugged in, which has continuously feeding in data, is yet to happen. But there are many scientists who have started doing it locally, which are like baby steps towards this vision. So I'm hopeful that this will become a reality very soon.
Wow. So we've gone from the very depths of time to the very future of our missions. And that's just a brilliant way to finish the episode. I really, really enjoyed those fun facts. And I feel like I've learned a lot more about the ocean. And I'd like to thank you both for your time today. It's been an absolutely brilliant episode.
Thank you.
Thank you.
Thank you for listening. This podcast was made by CEFAS, the Centre for Environment, Fisheries and Aquaculture Science. To keep up to date with us, follow us on social media using @CEFASGovUK. We hope you can join us again next time.